Now, the only tricky part of triple integrals is to try to understand what they mean. So how to visualize what they are telling us. And that's why I really wanted to focus on calculating area of a plate and total mass of a plate using a double integral. So now we can do the same thing in 3 dimensions. So calculate the volume of a cube. So the way you can calculate the volume of a cube is by saying that it is the triple integral on the volume V of the dV, the differential of volume. Okay. So for example, if it's a cube with size like I drew here on the top right, so then this would be equal to A, B, C, D, E, F of dx, dy, dz, which is equal to dV. And if you do these 3 integrals, one inside of the other, the final result will be b minus a times d minus c times f minus c, which is the product of the 3 sides, which is equal to the volume of the cube. Okay, so that is very simple, a very simple example. If the volume V was not a cube, it was some other complicated region, which we will do later in the chapter, don't worry, then you can use this expression to calculate the volume of funny shapes. For example, the volume of a sphere, you can do the triple integral to calculate. Now, you could also calculate, so this is a very simple case when the integrand is 1, right? So remember, here it's as if we had a 1 there. So it's a very simple case. But you can also calculate the mass of an object. In 3D space. Okay? So now this time we have some object which has some arbitrary shape, and this is in 3-dimensional space. Okay? And this has a certain volume V, and it also has a density, which for volumetric densities we usually use the symbol ρ, which is measured in kilogram per meter cubed. This is now the proper 3-dimensional density, which depends on position. Okay? So now the total mass is going to be equal to the triple integral along the volume V of the differential mass. And what is the differential mass? Well, that's like imagining that you select a tiny differential cube, yeah, and this differential cube has a mass dm. And since this cube is differential, you can assume that dm is simply the density evaluated at the point corresponding to the cube times the volume of the cube, which is dx times dy times dz. Okay, you can pretend that the density is constant because this cube is differential. It's so small that you can pretend that the density is constant. So that mass is equal to density times volume. So now you can substitute that into dm, and you get that this is the triple integral along a volume of the density, which is a function of x, y, z, times dx, dy, dz. Okay? Which you would have also written as dv if you wanted. And notice that the units always match. So this has units of kilogram per meter cubed. dv has units of meters cubed because it's dx, dy, dz, where each of those has units of meters, and therefore the total mass has units of kilograms. Okay? So that's the way you have to imagine triple integrals. You have to imagine dividing some object into an infinite amount of infinitely small cubes, and then adding up some property of those cubes. For example, the mass of those cubes, dm. Yeah. So that's why I warned you to not to try to forget the idea that an integral was an area under a curve, because, okay, this works for 1 dimension. It also works for 2 dimensions. But then in 3 dimensions, you can no longer picture it this way. Okay. However, the picture of dividing of the double integral being simply the division of a plate into small mini plates, and then adding something, some property of those mini plates, this always works for 2 dimensions. Unfortunately, it also works in the case of 3 dimensions, imagining mini cubes. So everything is made up of mini cubes. So you can add up some property of those minikubes. It can be the density times the volume. Maybe you are calculating the total electric field produced by a distribution of charges. So you could imagine you divide that distribution of charges into mini cubes of a differential of charge, and each of those mini cubes is producing an electric field. So you can add up the electric field produced by the infinite amount of mini cubes. So you can see that suddenly all of physics can use triple integrals to calculate all sorts of things. In electromagnetism, in classical mechanics, in everything, okay? And remember, we are limiting ourselves to integrals on x, y, and z. But these can be any three variables. So maybe they could be x, y, z, and time. And then you would have a four-dimensional integral, and so on, okay? So I hope you appreciate the beauty of multiple integration and how it can be so useful, okay?